Dear students, this is our ninth lecture on stereochemistry and fifth lecture on asymmetric synthesis. As I've told you, asymmetric synthesis is defined as a reaction in which an achiral compound can be converted into a chiral compound, uh, and this type of synthesis is called as asymmetric synthesis if the amount of stereoisomers which are produced, they are unequal. So if they are formed in equal amounts, then we say racemic mixture is formed. If they are formed in unequal amounts, that means the overall there will be an optical activity in the compounds which are formed. So asymmetric synthesis will be that when an unequal amounts of stereoisomers they are produced and the product formed is a chiral product from a achiral substrate, then such type of reaction is known as asymmetric reaction, and such type of synthesis is called as asymmetric synthesis. And common example of these types of reactions is, say, reduction reactions. In case of carbonyl compounds, they can lead to the formation of chiral compounds, and sodium borohydride reduction is the most common example. Similarly, Grignard reaction can also be used for asymmetric synthesis when carbonyl compounds they are reacted under Grignard conditions. We know that alcohols are formed, and these alcohols formed they can also be produced with unequal amounts of stereoisomers, so optically active products can be formed. Similarly, hydroxylation of carbon-carbon double bond can lead to formation of diols, and if these groups attached to alkene they are different, then definitely we can get the chiral products. Or hydroboration oxidation of alkene can also lead to formation of alcohols which can be optically active, and then these condensation reactions, which are the most common reactions, aldol condensation, can also lead to the formation of diastereoselective products. Then this asymmetric synthesis can be of two types: partial asymmetric or absolute asymmetric synthesis, which we have already told you in our third and fourth lecture. And the type of methods which can be used for partial asymmetric synthesis, they can be by using chiral substrate or chiral auxiliary or chiral reagents and chiral catalyst. And in our third lecture we have described the different types of first generation methods where chiral substrate is used for the asymmetric synthesis, whereas in the fourth lecture we have discussed some of the methods where we use chiral auxiliary for the asymmetric synthesis. And in the fourth lecture these four types of methods we have described, that is using proline or prolinol based chiral auxiliaries, or chiral imide systems, or chiral enamine systems, or chiral hydrazone systems as chiral auxiliaries. And in this lecture today we will see these four types of methods or systems which can be used for asymmetric synthesis, that is use of oxazolines or acyl sultanes or chiral acyl iron complexes. They are also being used commonly these days, or chiral enolates where they are double asymmetric synthesis. For example, in case of aldol condensation, these types of enolates they can be formed. Now first is use of oxazolines as chiral auxiliaries. this oxazolene system, which can be easily prepared from 2-methanol when this is condensed with carboxylic acids or their derivatives, then we can easily prepare these types of 2-oxazolene systems. And these 2-oxazolene systems, they act as potential precursors for the synthesis of chiral carboxylic acids. Now, basically, what is done is that we undertake the metallation of these types of 2-oxazolene systems when these are treated with a strong base like n-butyl lithium at very low temperature of the order of minus 78 degrees centigrade. Then we know that two types of azienolates, they can be formed, Z azienolate or E azienolate, they can be formed. But because of the unsymmetry present in these types of oxazolene system, one of the enolate is formed in more amount in comparison to the other enolate. And then these azienolates, they undergo alkylation reaction with say ethyl iodide in the present case, and this will lead to the formation of these types of intermediates which on hydrolysis will give us alpha alpha disubstituted carboxylic acids, which are chiral in nature. So we can see over here that from from chiral auxiliary, we can synthesize these types of chiral compounds. And we can see that here the product is formed with 78% enantioselective enantiomeric excess, and major product is formed as 2s product. Then the same oxazolene methodology can be extended for the synthesis of natural products. For example, the synthesis of European pine safflower sex pheromone, that can be achieved through asymmetric synthesis of these types of alpha substituted carboxylic acid. And this alpha substituted carboxylic acid through some common organic reactions then can be converted into this type of natural product. So basically 2-oxazolene system is first react with the strong base like lithium diisopropylamide, which will lead to the formation of a mixture of Z and E enolates, and those Z and E enolates, out of those, one will be formed in major amount based on the stereochemistry, and then we'll add to the alkyl halide. In the present case, N-octyl iodide is used, and alkylation will take place at the alpha position, and we will get these types of oxazolene intermediates, alkylated intermediates, and these on hydrolysis will lead to the formation of carboxylic acids. So alpha methyl carboxylic acids, they will be formed with 72% enantiomeric excess. Then these carboxylic acids on reduction with lithium aluminum hydride, on lithium aluminum hydride in presence of toluene sulfonyl chloride and pyridine will lead to the formation of alkyl halide. And this alkyl halide on reaction with these types of lactone will lead to the formation of these types of sex pheromones on reaction with hydrazine in KOH. So reduction will take place and we will get these types of products. Similarly, these oxazolene derivatives they can also be used for the synthesis of different types of alkylated carboxylic acids. Here, the alpha beta unsaturated oxazolenes, which are prepared from two oxazolene derivatives through these two types of reactions. First type is that first this two oxazolene derivative will react with this base this or butyl lithium, which will form the enolate, and then this enolate on reaction with aldehyde will undergo aldol condensation, and we will get these types of intermediates, and these intermediates will undergo dehydration at this place to give us these types of vinyl oxazolenes. Similarly, these vinyl oxazolenes they can also be prepared through this route also, that on reaction with LDA followed by diisopropyl phosphorus oxychloride, we will get these types of intermediate, which on reaction with aldehyde will in presence of a strong base will lead to the formation of vinyl oxazolenes. And these vinyl oxazolenes then will undergo addition reaction at this carbon-carbon double bond in presence of alkyl lithium to give us these types of two oxazolene alkylated products. And these intermediates they will undergo hydrolysis to give us alpha substituted carboxylic acids as the product. And depending upon this R and R1, the enantiomeric excess of the product formation is affected, and configuration of the product formed is also affected. So if this R is say methyl group and R1 is ethyl group, then R product is formed. But if we change from alkyl to phenyl, R1 is phenyl lithium, then the product formed is S. So this is because of the stereochemistry of the intermediates which are formed from the alkylation of this carbon-carbon double bonded compounds. Then oxazolenes, depending upon the type of other substrates which we use, can be used for the synthesis of different types of organic compounds which are chiral in nature, and most commonly used synthesis is synthesis of optically active alpha alkyl alkanoic acids. So these types of compounds are alpha alkyl alkanoic acids. Then alpha hydroxy alkanoic acids, they can also be prepared alpha hydroxy carboxylic acids. Similarly, we can synthesize beta hydroxy methoxyalkanoic acids and other types of beta substituted carboxylic acids. They can also be synthesized. Similarly, we can synthesize alpha substituted gamma butyrolactones from different types of substrates, and similarly these types of lactones they can also be synthesized. The next is acyl sultan systems. In most of the cases, N-substituted sultans, N-acyl sultams, they have been used for the asymmetric alkylation to give enantiomerically pure alpha-alpha disubstituted carboxylic acid derivative. Basically, these types of acyl sultams they can be easily prepared from this sultam derivative, which is a chiral molecule, and this is very cheap and inexpensive. So by acylation of N-acylation of these, we can prepare these types of chiral auxiliaries, N-acyl sultanes. These N-acyl sultanes, when they are reacted with metal ligands, they are converted into these types of Z-enolate intermediates. They are preferably formed the Z1 because here this stereochemistry is more stable in comparison to E stereochemistry. So this Z-enolate intermediate then through RE phase adds to the alkyl halide to give us these types of alpha-alpha alkylation products. So these alpha-alpha alkylated N-acyl sultanes, then they can be hydrolyzed or oxidized uh, to give us the hydrolysis of this bond to give us carboxylic acids, or the reduction of this bond followed by hydrolysis to give us alcohols as a product. So alpha alpha disubstituted carboxylic acids or alcohols, they can be synthesized using N-acyl sultanes as the chiral auxiliary. Similarly, this N-acyl sultam or the sultam can be used for the synthesis of anisomerically pure amino acids also. So here, instead of N-acylation with carboxylic acid derivatives, these types of methyl and bis-methyl thiomethylene glycinate derivatives, they are used for N-acylation to give us these types of glycinate sultam derivatives. So these glycinate sultam derivatives, they can be used for the precursor of various types of alpha amino acids. So basically what happens is that these glycidate sultam derivatives, they react with strong bases to give us these types of chelated Z-enolates as we have seen in the previous case. And here now instead of RE phase, they undergo alkylation through SC phase of the alpha carbon, because this is opposite to the lone pair of electrons on the sultam nitrogen atom. So in this way, on reaction after the alkylation, these types of intermediates, they are formed, and these intermediates, they undergo acidic hydrolysis to give us amino acid intermediates. And these amino acid intermediates, through the removal of this sultam moiety, can be converted into pure, isomerically pure alpha amino acids. And here we can produce purity level up to 99.8% of enantiomeric excess. So here we get S enantiomer of the amino acid formed through these types of reactions. When the R is either methyl or benzyl or allyl, we can prepare different types of alpha amino acid through this type of method. Then this methodology can be extended to other types of diastereomeric carboxylic acids. For example, this can be used, sultam can be used as an excellent chiral auxiliary for asymmetric carbon-carbon bond formation, reactions like aldol condensation or other types of organic functional group transformations, where we can get different types of 1,4 addition reactions to give us optically active products, diastereomeric in nature. For example, if we react sultan with alpha beta unsaturated carboxylic acids or their derivatives like halides, then we will get these types of alpha beta disubstituted E sultans. So here the configuration is E, and these alpha beta unsaturated carbonyl compounds, they can undergo copper 1 chloride catalyze 1,4 addition of alkyl magnesium halides, and there is a possibility of formation of these four diastereomeric compounds. They can be formed, and it has been found that out of these four, this is the major product which is formed in 86.3% amount, and then after hydrolysis this can lead to the formation of these types of alkylated carboxylic acids as the product. And we can see that anisomerically pure alpha alpha disubstituted carboxylic alpha beta disubstituted carboxylic acids, they can be synthesized in this manner. The next methodology is use of chiral acyl iron complexes for the synthesis of alpha substituted carboxylic acid. So when this chiral cyclopentadiene triphosphonium iron complex, this is reacted with n-butyl lithium, this hydrogen present at these carbons, they are acidic carbons, and enolization will take place at this. And here the major enolate formed is E-enolate, because here one of the phenyl groups of the triphenyl phosphine that will block effectively the approach of the electrophile from the Re phase of the C2. So the alkylation of this E-enolate will take place from the C phase of the complex to give us these types of complexes as intermediates. And these complexes on further removal of iron, they are reacted with bromine water. So in presence of bromine and water, they are converted into optically active anisotrophic alkylated alpha alkylated carboxylic acids as the product. And here also the products can be synthesized with high degree of anisotropicity. Then is chiral enolates. The most commonly used reaction for these types of synthesis is aldol reaction, and here also we can use these types of valine based chiral auxiliaries as the starting materials for the synthesis of aldol products. So when these are reacted with boron based enolates, the chiral boron enolates, they are formed, and because of the stereochemistry of these enolates, Z enolate is preferred, and then that this Z enolate adds to the other carbonyl compound to give us these types of intermediate aldol products, which on hydrolysis gave us the aldol products in anisomerically pure form. So these are the references which have been used in preparing this lecture. Thank you very much.